we are going to talk about how two observers can experience the length of this moon differently. So we'll say that this is the moon of Endor, and this is a TIE fighter going at 90% of the speed of light, and this is some observer at rest on a planet. Maybe it's Endor, I'm not sure. But anyway, so it would make sense that the pilot of the TIE fighter, if he had a stopwatch and he measured the time that it took him to go from the left side of the moon to the right side, he could multiply that by his velocity and get the distance he traveled, right? So the time that he perceives that it took him to travel from one side to the other times his velocity. This guy at rest, he can agree that the TIE fighter is going at a 0.9 c relative velocity, 90% of the speed of light, but he doesn't actually agree on the amount of time that it takes for the fighter to go from the left side to the right side. It's the crazy thing. Time is relative. Both observers will. It's not like one is right and one is wrong. Both are correct. I mean, both are have valid observations, but it takes a different amount of time. For that same event for each of those different observers, and here's why. The only thing that all observers can agree on is the speed of light. The speed of light is the speed of light, 3 times 10 to the 8th meters per second. Everybody, no matter how fast they're going, in whatever direction, they're all going to measure the speed of light to be that value. So when the pilot of the TIE fighter, maybe he has a pocket laser, and he shines it from one side of his cabin to the other, it takes a certain amount of time for it to get from one side to the other for him. But that same event, the laser going from the bottom to the top of his cabin to the observer on the ground, it actually looks like the laser is traveling farther, because during the time it takes for the laser to go to the bottom to the top of the cabin, that TIE fighter's moved across the sky. So to the observer on the ground, it looks like the laser's gone from here in a diagonal line up here. And if both the pilot and the guy on the ground agree that the speed of light is the speed of light, light traveling farther must take longer to do so. So for the guy on the ground at rest, the light traveling, for him it looks like the light traveled farther. Therefore, that event of the laser shining across the cabin must have taken longer than for the guy in the TIE pilot. Because for him, the light only went from here to here. It didn't go as far, but they both measure it to be the same speed. So an event where it doesn't go as far is an event that doesn't take as long. So the pilot's experience of the time to go from the left to the right side of the moon is going to be shorter than the time experienced by the guy on the ground for that same event of the TIE fighter going from the left to the right side of the moon. How much different are those times going to be? They're going to differ by the Lorentz factor. This is the Lorentz factor. This is the relative velocity between two observers. This is the speed of light. So for our person at rest, the same event seems to take the Lorentz factor times longer. here I have just substituted delta t with the Lorentz factor times the naught. Remember, t naught is the time experienced by the pilot. Now we just have to figure out what is gamma. What is the Lorentz factor if you're going 90% of the speed of light? Well, it's 2.3. Now, but notice here that gamma ranges from 1 on up, and if it's just 1, that means there's basically no relativistic effect. Both observers, if somebody's going 1% of the speed of light, both observers are going to experience time to pass the same. It doesn't, relativistic effects don't really kick in until you're going like about half the speed of light. So we can take that Lorentz factor of 2.3 and pop it in here, and now we can compare the length of the moon that the pilot experiences to the length of the moon that the guy on the ground experiences. Of course, the guy on the ground, to him it looks like a normal moon. It looks like a sphere, but this is the normal length of the moon that where it looks normal. But look at compared to this, the pilot sees the moon to be 2.3 times shorter than the guy on the ground. And here's so that's the relativistic length contraction. And the thing is about that length contraction, it's only in the direction of motion. So he's going left to right. The moon doesn't appear to shrink up and down for him. So it's still, to the pilot, it still looks, pretty long up and down wise, but not right to left wise, because that's the direction he's traveling in. So it looks 2.3 times shorter left to right.